Yeah, I guess Sami, you're here also. Yeah, okay, I hope the recording it says it's recording, but this Zoom with the multiple hosts is really sometimes confusing. Okay, so okay, so Sami, yeah, if you can take care of the recording, yeah, that will be nice. Thank you. Okay. Right. So yes. So yesterday, Pauli was talking more on the, let's say, possibilities and also limitations of a quantum computing, but we didn't discuss too much yet the actual algorithms. And actually, we are now going to discuss a few of these cases. Something we already started last week, and well. You have to be excused me if my explanations are not always very clear or if I cannot provide the answer in real time. But if anything feels strange or unusual, or if you have questions, please simply feel free to also contact by email, and I will try to then clarify perhaps in the next week. We still have 2 more lectures next week. So I mentioned this because, now we are getting towards the end of the contact teaching or this lecture part of the course, and this lecture material will necessarily be a little bit more improvised, let's say this way. So I'm not I don't consider myself an algorithmics researcher, but more like an yeah, if I would have to categorize, I'm more of an electrical engineering plus computer science mix. In that sense. So, and I'm also just like you, I'm trying to get the basic ideas of this quantum algorithms. So what is this all about? So what this means that today I'm not going to be necessarily going to very much detail in this algorithm, but more that I try to give some of the key ideas, key ingredients of this, let's say, building blocks of this quantum algorithms, and hopefully those of you who haven't got yet decided their project topic, perhaps you will get some ideas here on what kind of methods you, I mean, if you pick an algorithmics topic, quantum algorithm topic, so what kind of methods you may be interested. So it's going to be a very sketchy presentation today and probably also next week, but I think we actually wouldn't have time to go all the details in this kind of short course in any case. But yes, so let's then go to discuss this one. So last week we kind of like started with something we call the Deutsch problem by David Deutsch, which was addressing the constant versus balanced problem. And well, this is an example of what we call the oracle problems or oracular problems, if you prefer adjective. So where these algorithms, the main purpose why we discuss this class of algorithms is that well, each one of them serves a particular, let's say, pedagogical purpose. Firstly, I mean, they are very kind of like simple algorithms in a sense, and they are bringing up particular points about the quantum computing. But at the same time, these oracle problems here are not really meant to be, you know, to be practical in a sense. They are only needed for the case of, let's say, demonstrating the potential time advantages of the quantum computing over classical computing. So sometimes you have an exponential speed ups, like in the Deutsch algorithm, and sometimes you are cutting a square root from the corresponding classical version, like in this Grover's search algorithm. So this first set of problems here, if you are not very, if you don't feel very fascinated about them, don't feel bad, because for me it's also the necessary things we have to discuss. But I would like to think more practically, hopefully, about the quantum computers. That okay, what can we do there, and rather than, let's say, working on this kind of like toy cases. But having said that one, yes, it's an introductory course, so we'll have to discuss some of this. So I think, well, we will we will today focus primarily perhaps on the search algorithms and well, at least starting or giving an idea of the Shor algorithm, which is something very famous in quantum computing. And well, this Shor's algorithm is something you know, it's relevant in the public key cryptography, for instance, all the communications. So historically, it was one of the one of the boosters to why the quantum algorithms are being studied, because it has so potentially very widespread implications to the society and so on. So I think at least we have to be aware of the what it is about. Right. So last week we talked about the quantum oracle. So I will repeat here briefly the idea what that was. So the quantum oracle was basically a kind of like construction that we need to build if we have an arbitrary binary function, let's say mapping a binary sequence to another binary sequence. And which may not be an invertible function. And for the quantum computing, you already know that, okay, we need to be able to have an reversible circuits, invertible functions. So this oracle was a kind of like way how to construct for any given f this kind of like reversible version, so that we can evaluate this function on a quantum computer. And well, to do that one, we had here this kind of like sometimes like extra data, what you may call a chunk bit or something like that. And when in this case, when we set it to be equal to 0, then we see that this output here is then emulating the original function f. And well, so why do we talk about the oracle? What it is? What is the idea behind? So, like I mentioned, in these cases, we are really discussing more on the what is possible with the quantum computers, and the oracle is simply if you're coming from a software engineering background. So perhaps one way to think about the oracle is just similar to an API call. Okay, so you have something like a software that you are using in your work, but you don't know actually what that software does internally. You only know that it does what it's supposed to do. Okay, so you can in that sense you can trust your library function or your API call that, okay, whenever you're calling that thing there, it's returning you whatever is that you wanted to do, but you don't know how it's implemented. So just if you are thinking about this, if the quantum oracle sounds strange, just think about the function call or library function call that you haven't implemented the function. Okay, as simple as that one. So one oracle query means, okay, having a one call to that function. And well, one reason why it's kind of like said to be in this kind of like black box mode, that we don't want to discuss how the function how the internals are, is that well, those kind of implementation details, you could have a differently efficient or inefficient ways of implementing the same thing. And well, maybe from a, let's say, from a linear algebra, like one example might be that, okay, you could compute, let's say, matrix product of some three matrices A, B, and C. And well, this could be, well, they could have different sizes, but as long as the internal these dimensions are compatible, that you are able to compute this one. So you could compute this in let's say in different orders. Let's say first the B times C, and then you multiply this matrix here with the A to get the matrix product. But mathematically, the same thing. You could first compute the A times B, and then this results in a new matrix, and then you could have this this result here multiplied with another matrix C. And the order in which you are doing these computations could make a difference. I mean, one of them could have a much slower way of computing this matrix product, leading to the same result. But if we think this instead as a black box, some matrix product here, you don't know what it is. But for instance, if you want to now multiply something like an matrix times vector, you would put some x here. Now you want to compute that one. So depending on how you compose these matrices, you could have a different time spent on what this function produces. Yeah, and in the end, it's just a one matrix in this case times some input x. But the point is that yeah, you could even put here have many more. You could have 1,000 matrices here multiplying each other, and still in the end, these 1,000 matrices would, because everything is linear, it would be still simply a one matrix multiplication with the x. And the point is that in this case, we are not interested really on how these computations internally are organized. So we don't care about the details of how whether or not the computation of this oracle is very fast or very slow, but we want to kind of like abstract away from the details that are not interesting to the problem. So that's why we are not considering what's the kind of like the computation time of that oracle itself, but more of a question. So how many times we need to call the oracle? So that is the idea in this oracle queries. So it's more abstract way of analyzing the algorithms and stating results about and proofs about the quantum complexities and so on. But it's let's say convenient way in this sense. Okay, just like that your friend, if you are implementing some program codes, maybe your friend is implementing the same thing, but in your opinion, it's too slow code or it's not so great. As long as you get the same result, the same correct result, what you get, it's fine. So no difference. Okay, so that was the idea of the oracle and why we are talking about these oracles in the first place. So now. Last time, I want to repeat here a few key ideas of the quantum algorithms, as I realized that last time my explanation was not very great. This happens when you're teaching some topic a number of times. So this is the second time you are now hearing this quantum computing course. So this year the explanation is slightly better than last year, but it's still not probably very good, but I will try to get these key ideas delivered, hopefully. So yeah, one of the key ideas, obviously in the quantum computing, is that okay, we want to do things in a quantum parallel way, right? I mean, that is one of the things we can do when we are using these superpositions. Okay. So, and well, here is just one example circuit to illustrate the idea. So that is we have the oracle, the unitary corresponding to function f, and then there is this 0 and 0 inputs, and then we have a Hadamard gate here. So if you already well, okay, let me ask this way. So do you remember what the Hadamard applied to gate 0 is doing? How do we call this state here? Just that you don't fall asleep immediately today. What is this state here? Or in other words, yeah. So yeah. Well, I think every now and then it's good to to repeat this. These things so that you start to memorize these things. So that is something like we had a shorthand this plus here because we got the plus sign here. So the Hadamard is here to create the superposition, and then basically after you apply the oracle in the way that everything that was defined here. So that's everything you need to know how the oracle is constructed. And when you apply it to this two inputs here, you can see that actually the expression of the function is you have both of the values, the f at the value 0 and f at the value 1 here in this state expression. So so that is the key idea of the quantum parallelism. You are kind of like we send here the single query 0 0. And now, as a result of this Hadamard and this quantum oracle here, we are kind of like creating or having information of the function, all the function values here in the same expression. So everything, it's a kind of like okay, you put the one single query to the Oracle here, but as an you get now out simultaneously this some information of the function values with value 0 and 1. Okay, and actually last time we did some of the computations here. I'm not going to be repeating, but I just included here some of the details for those who are curious. I mean, who are not convinced or want to check. So today you don't have to take the pen. I give here the answer, and well, it's just the computation similar what we did last week. So I'm not going to repeat here. So. Well, okay, maybe I can actually mention one thing here, which might be new to you. Is that well, so when we have an like when we analyze a circuit like this, so let's say we have here the state 0, 0, the tensor of these two states, and it goes to Hadamard, and well, we do nothing here on this this second qubit. So in that case, well, you can still think that, you know, there is the invisible identity matrix here, you know, kind of like do nothing operation here, like in terms of the mathematics, what's happening. That's how you can how you can think about. I mean, I shouldn't put it even in a dash box, you know. You could with that's what we have here. So we are just not drawing this identity transformation here. And then how you then, let's say, analyze expressions like, okay, so 0, 0 goes to block like this. So here comes one of the things about the property of the this tensor product. So which states that if you have let's say two matrices A and B, okay, and we take actually, well, now this is the tensor product of matrices. Okay, I already start to regret I wrote this expression because I will not explain what it means, but basically whenever you have an let's say expression like this, that okay, there is some tensor product here, some tensor product here, and matrices A, B, C, and D, and then this one right here is well, this is a conventional matrix product here. Okay, so and these were the tensor products. So in that case, how this kind of expression can be rewritten is that, okay, we actually can take the matrix product of this A times this C here, and then we're moving the tensor here in the middle. So this is the same as A times C, so matrix product of A and C, tensor B D matrix. And well, okay. I mentioned this one because, for instance, in this step, we are actually using that kind of idea. So now we know that this is the input state 0, 0, and now we want to kind of like say that, you know, apply the Hadamard to the first one, the first state, and apply the identity matrix to the second one. So that's what we got here. So it's times the this kind of tensor 0 here. So sorry, I'm writing garbage here. Well, okay, you can see it actually here. So here the Hadamard is applied to the first one, and then the identity matrix is now applied to the second one. So, you know, it's the same as the tensor of this Hadamard and I matrix applied to the tensor of 0 and 0. Okay, can be a little bit confusing, but again, it's just algebraic rules. And by applying this kind of rules, you can see here the quantum parallelism coming out here. So that's the point of this kind of analysis. Okay, fair enough. So that was the quantum parallelism. So the other key idea that is important in many of the Oracle algorithms particularly is this phase kickback that we already discussed. And well, just to remind what this means is that, okay, we have again the quantum oracle defined in this way. And now we let's say we are putting here on this second input, we put the minus state, well, created again using Hadamard on the 0 state, the 1 state. And now after you apply the oracle, the point was that the whatever you had the knowledge of the function is now kind of like kicked onto the first wire, in particularly in its phase term here. So meaning that, okay, we have something like -1 to the power of the function value, which is either 0 or 1. So this is either -1 or +1 here in the end. So what it's doing is that it's kind of like then well, flipping the sign of this x here. So modifying the phase of this original x. And well, last time also that's something like we already did on a paper to see how this comes up. But if yeah, okay, I mentioned this one. So and again, like if you are not convinced, this is just a summary with some details that I added there. If you were not so clear last time what we did there, so I will not go through the explanation we did it last time, but this just to clarify how the phase kickback works, and it's again just raw computation, nothing else, no quantum magic. Okay, so then when we have this quantum algorithms, so the third key idea is kind of like summarized that the kind of like blueprint for many of these oracle algorithms is the following. So which you already saw in this Dodge algorithm, is that, okay, you first prepare some inputs. Well, it's usually just a 0 or 1 depending on what we do here, and then we use this Hadamard gates here to create the superposition. Okay, we could also say, okay, we are opening the superposition here, or if you prefer, that's when we are sending our inputs to the parallel evaluations. In a sense, yeah, when we call the oracle. So this creates superposition, and together these two are now doing the parallel function evaluation. And now the computation is then ended by applying again Hadamard gates. So this is kind of like to now come back from the superposition to one of the definite states, and well, we measure in the end to read the result. So so yeah, this is I mean this general kind of like design principle holds for many of the algorithms, including the ones that I listed there, apart from the Grover. But yeah, this is kind of like still the general idea. So if you remember this idea, you can get some kind of sense what's happening in these different quantum algorithms. Obviously the devil is in the detail, like always. So yeah, so for instance, this Dodge problem and the Dodge-Choska algorithm. So that's something like we already discussed last time. So that's the particular circuit that we would need here. Guer it with this one particular inputs, and then after the measurement, if we are reading 0. We have some results, and then the opposite of that one if we read 1 as the solution. Okay, I hope that this clarifies a little bit the kind of like the building blocks of the quantum algorithm. So yeah, quantum parallelism, the phase kickback, and then this general design principle where you put the oracle in the middle and Hadamards to open and close the superposition around that one, followed by measurement. Okay. So now let's then move to this search algorithms. So this is possibly more interesting than this Dodge-Choska method. And well, the way how these problems are often presented is that, okay, we are searching a needle from a haystack. Okay, so as we know, this is I don't know if any of you have literally done this, probably very difficult. But maybe here is a more familiar analogy. So so imagine you have a actually Excel telephone book. So maybe most of you are too young to remember when we actually used to have these huge books printed, and if you would need to, I need to figure out how do I call to someone. There wasn't the internet in the 1980s, so you would open your book and find there, okay, I know that's the guy I'm looking for, or that's the company I'm searching for. So you look up here the name, and which is sorted in alphabetical order, and you look up the phone number, and there you go. You call to that number. No Google cheating, just a phone book. And yeah, so this is easy because you have this book comes in a sorted order according to the alphabetical listing. But the inverse problem is much more harder. So if someone gives you a phone number, that okay, who is the owner of that phone number? Well, you are in trouble because you have to basically, with the brute force searching, you cannot do anything else except look for the numbers one by one, and then once you will find it, you will hope that okay, now yeah, that's the name that corresponds to the that given number. So that is what is known as a kind of like unstructured database search. We cannot take leverage from the structure of the data, but we have to do brute force searching here to find what we want to find. Okay, so yes, and by the way, I forgot to mention something about this Oracle problem. So this is sometimes called also like these general problems are called something like promise problems, which means that there is certain guarantee of the function that we are that we are learning about. Like for instance, in the constant versus balanced, we are promised that okay, this function will be either one of these two cases. There cannot be any other cases. And likewise, in this kind of like telephone searching idea, well, we would be guaranteed that, okay, we know that this number belongs to someone, so it's somewhere in the book, and there is going to be only one person or company that owns that number, but we don't know where it is. So that's something like a promise problem. And well, if we would have something which is not in the phone book, that would be outside of the scope of this kind of problem. Okay, so obviously here the phone book is just an analogy, and generally speaking, you could have any kind of like thing you are searching using some function. And here again, the idea is the same as in the previous one. So we are making kind of like Oracle from this function, and this Oracle, the function call here now tells us that was it this one here? No. I'll move to the next one. This one, and finally, once you will see the one you are searching, then we get the response yes or true or found. So so that's how it works. So here is then the general version in a more like in a more familiar computing language. So we are given an array of let's say n capital numbers, and well, we know that somewhere in this table is the item we are searching for, okay, which I indicated here by X star. And well, the task is to find this index here. Yes, and well, this is already something I mentioned, so that would be kind of the Oracle function here this time, or the function that where we can ask the question. So given X, is it this one or not? So so this is actually we've been talking about the Boolean functions, and this is another similar task. So so if you think about the table indices in binary format, so in this case, for instance, we got 8 table entries, and well, with the that contains all the possible 3-bit strings there. And so in that sense, you can think this task as a brute force way that you have to kind of like enumerate all the possible 2 to the power of n indices that correspond to the decimal indices shown there to find the item you are interested about. Okay, I think I just said that one. Yeah, and just to mention about the notational convention, if you are reading these quantum computing books. So here, when we indicate by the small n, that's usually the number of bits that we mean the size of the bit string, whereas the capital N is then to the total number of states, which is the 2 to the power of n, as you know. Okay, so now something hopefully very familiar to all computer science students at least. So if we are given a structured search problem, Pauli also mentioned yesterday about the structured and unstructured search. So in a structured search, we are also doing this kind of searching from the table. That okay, we know that there is entry named 76 somewhere in this table, and the further information we have is that okay, this table is sorted according to the values that are stored in. So everyone knows how to do sorting, like quick sort or bubble sort or whatever you may want to use there to create that kind of ordering for the table. And well, in the when we do this so-called binary search, I hope everyone knows what it is. We are kind of like looking first from the middle of the table. So let's pick in what is in this table number entry 4. And well, it wasn't the one that we are looking for. And now we know that okay, it cannot be to the left-hand side because we know that the table is sorted. So it has to be on the right-hand side because okay, everything is lower than 14 to the left. So that excludes these states. So now you go to the right and again, you exclude, okay, we know it cannot be the one of the last 2 items. And now you located this one here. So I hope this one is very familiar to everyone. Just good to repeat every now and then. So I will skip here the details, but you will, if you're familiar with the binary search, that's how you can figure out how many queries, how many times you need to actually check the table entries to figure out to find the element you're interested. And it appears to be the base 2 logarithm of n number of times you need to check the table entries. Okay, and whereas the unstructured search, so just repeat it. Now we have no idea of the structure of this data. It's just that it's the haystack or the phone book where we are now searching the name for a given number. So that's I think here is the brute force. So you have to check everything one by one if there is no other further information about the structure in the data. Okay, maybe here just a refresher. So for this unstructured search, can one of you tell me how many queries we will need here to find the one with certainty? I mean, from the table. You could give the worst case or the average case, depending on if you remember how expected values work. So if we have a table with n entries in the unstructured case, okay, there is proposal n squared. Any other proposals? Anyone? So this is just something okay, quantum, yeah, square root of n. That's right. We're gonna be getting there, but this is not still on the classic case. In the classic case, without any quantum things. Anyone? Okay, thank you, Max Granlund. So n sounds like a good answer, and well, because that's what you will have to do. Like, okay, we already know it wasn't here. And until the worst case, you'll have to check the last item. So in the worst case, you will have an n queries. And Also, in the average case, I will skip this one, but let's say, well, let's just briefly discuss the idea. You know, it could be that that's the place where you find your item, and this happens with the probability 1 over n. You know, it could be anywhere here, but the probability that it would happen to be right here in the first element equals 1 over n. That's the one that you are looking for. Likewise, for the probability that, okay, we would find it from here. Also, okay, let's say, well, probability to find, well, I think we marked by x star, and so on. And it's basically the same probability for all the positions here, 1 over n for everything. And then if you know how the expected values are working, well, this just for those who have studied statistics now, let's maybe you will feel very nice about this one. So you will have something like the expected value of random variable x is that, okay, you are going through all the possible, let's say the values in the range of this x, and then you have the probability that your random variable is taking this particular value x. If you don't know this equation, don't worry, it's not important here. But basically, from applying here, you will also find that okay, it's something like on average we will need half of the half of this n here. But as you know, in computer science, we don't care about the constant factors there, but like what Pauli was talking yesterday. But instead, we say, you know, this is on the order of n, and same holds for also for the average case. So in both cases, you will need the on the order of n times to check the table, but in the worst and average case to find the item. So and so you may think that, okay, perhaps in the quantum computing, because we don't have any idea of the structure of the data, so perhaps we also, you know, how on earth could we, you know, cut down this kind of like brute force searching to something better. But that's actually what something we can do. And let's see if I'm able to summarize the idea or not. But before that one, so to sum up the previous discussion, so basically, if you have a structure in your data, like in this case, if we have the table in a sort order, then these failure cases are helping us to kind of like steer the search to the correct direction, and then we can cut the number of possibilities that where the item cannot be found. Whereas in the unstructured search, you know, the failure cases don't actually help us at all. But in a quantum world, they actually do. And again, the idea is what was already mentioned. So what we are going to be doing is to send a parallel queries to create superposition. And then what we are going to be doing is kind of like going to be systematic way of increasing the probability of the item that we are looking for, the marked item, and at the same time to decrease the probability of all the rest of the elements. So that sounds like a very intuitive. I hope that eventually you start with something like you don't have no idea where the item is located, but then you are kind of like fiddling around with the probability amplitudes and trying to increase the probability of the item that you are searching, and reducing the rest. And let's see if we can somehow like get some intuition how this works. Okay, let's see. Okay, so almost 1 o'clock. So yeah, I think I mentioned the idea, but yes, so that's that's summarized it in a quantum computing language. So here you have your possible solutions, which are again the binary strings. So we are kind of like searching over this space, in this case 8 possibilities, and we know one of them is going to contain the marked item. And then at the beginning we create equal superposition. You know, all the 8 states here are equally likely. So what you have here, I have drawn here basically a histogram, if you're wondering what these green things are here. So it's just a picture of that that presents the probabilities now, not the probability amplitudes, but the actual probabilities of these different states here. And yeah, so that's what we initialize. We have initially no idea where the item is located. And then what we're going to be doing here is to kind of like create an iteration so that okay, you know, after the first one, you will say something like this: the correct one jumps a little bit up, and the other one's down. And then after some number of iterations, you are amplifying the correct solution and de-amplifying all the rest. And you do this a number of iterations, and at the end, then you collapse your measurement. So even, let's say in this case, you would say that, okay, with the high probability, when we measure, we would be outputting this state here, and then we know in which index the one that we're looking for can be located. So that's the key idea of how this quantum search or the Grover algorithm works. Yeah, and this is known as amplitude amplification. So, okay, it seems it's almost 1 o'clock. So let's actually see whether you want to have a break here. So let's see. Okay, I think I see sufficient evidence for enough many people wanting a break. So, okay, I start to regret that I always put the 3 options here. I should just put yes or no. But yeah, the winner is the short break. So so yeah, so then in that case, so let's have here around 10 minutes break. So we will continue 8 past 1 o'clock, if my clock is correct. Okay, so see you in 10 minutes. Okay, so let's continue. Well, this time I start with the short poll here. You can see there. You will learn in a moment why I ask this question, but yeah. Okay, most of you are familiar with Google Colab anyway, but some are not. Well, you will see in a moment. So I will this time I will not be using any IBM Quantum or anything, but we just, let's say, I was convinced about these search ideas using just plain Python language. And yeah, okay, so most of you are familiar with Google Colab, but if no, don't worry, you will learn it in a second. So yeah, so that was the idea behind the what we want to do in the quantum search. So now let's get to a slightly more detail. So how to get this done? Okay, this superposition. Well, no need to talk about this one. So so basically in this Grover iteration, there are 2 kind of like steps that we are alternating with. So it's an actual algorithm. Okay, so you have 2 steps and you're alternating between 2 steps to kind of like get to do this amplitude amplification that you saw intuitively illustrated. So let me show what are these 2 steps. So the first one is something we call the phase inversion of the marked item. So meaning that if, well, let's say that these are your the probability amplitudes. So in this case, we have a search space of 4 elements, and let's say the third one is the table entry that we are looking for. And this is the initial equal superposition presented by this probability amplitude vector. So yeah, if you are wondering why they are 0.50, so again, if you still remember how we define the probability amplitudes, so well, okay, we score the probability, the modulus of the probability amplitudes, and that has to equal 1. So we got the 4 cases. So in this case, these probability amplitudes are 0.50 in this case. Yeah. So as simple as that one. So all the other probability amplitudes now remain unchanged, but the one that we are looking for gets flipped in the sign. So 0.50 becomes minus 0.50 in this case. So that is what we call the phase inversion step. And then the second step that is done is to, again, like very simple. So now you got your vector, or table, if you prefer, of the probability amplitudes here. Now what we are doing, you find the average value of all the probability amplitudes in the table. So average of everything. And then what you will do, you will update your probability amplitudes by this kind of formula: 2 times the average minus whatever value you had originally in the table entry. So to use this example here again, we find that the average of the probability amplitudes is 0.25. And now if we simply apply the formula that you shown there, what you will see here is that all the other amplitudes, apart from the one that we were searching for, get zeroed out, and the one that we searching gets to equal with the 1. So now if we would measure this state here, measure this system, so we would end up with that state here with the probability 1. So in other words, we would have found the correct item. So of course, if you are like myself 1 year ago, you are wondering here, wait a minute, so what do you mean that, okay, we mark the item that we are searching for, isn't that what we don't know? And for some reason I've indicated here that, just take this correct one and flip the sign. You're right, this is very strange. And so here I'm not going to be talking yet how we implement this kind of thing without knowing the answer. But here I simply want to get you convinced that, if you take these 2 steps, that if we are now iterating between those two steps, that eventually it leads up to what we saw in the picture. So something like that happening. So now let's actually stop the death by PowerPoint and let's start do some coding. I will share the link here in chat. So okay, wait a minute. So there you go. You should be able to open this link, but if not, let me know. Maybe Sami or anyone can confirm if this link opens. Okay, yeah, so okay, thank you. So it seems to work. So yeah, so let's I created here just this very simple example. So suppose now that we have a table of size 64 entries, so something manageable just to work here. And well, as mentioned previously, the small and the capital N are related like that. So 2 to the power of small n is this capital N here. So we have n small number of bits and a capital N number of possible states. Yes, and yeah, so for those who are not familiar with Google Colab, so you can see here what we are doing is just simple, very intuitive web interface. You could make your own code by, making a new notebook, but basically this play button here will then run your Python code. So you don't have to install anything, no Python, no libraries, anything, just include here whatever is that you want to do in your code. I have to say it's a fantastic tool especially for teaching and even for some research purposes. So if you are not familiar with Google Colab, it's a very nice way to get familiar with this kind of notebooks and Python. Yeah. So okay. So but let's then see what we are doing here. So yes, this is my table size, And now I'm let's say I'm the oracle here now, and I tell that the item we are looking for is going to be located in number 17. So in reality, we don't know this one, but as said, we just want to get convinced that the 2 iterations that we showed there is doing what it's supposed to do. So well, okay, let's actually just see what this code does here, and then so on your end, feel free to simply run the code by clicking that button there. So let's see if this works. Yeah, it sometimes takes time, but yeah. So then what you will see in this picture is now the all the possible states are in the x-axis. So this is what you can think about the table indices. And then the bars here are showing the probabilities. Sorry, the probability amplitudes of the of all the states. Or actually, let me check what we are graphing there. Yeah. So yes. So this is actually probability. Yeah. The amplitudes here. So it's the 1 over the square root of n, the one that you have seen often in the front of the expressions already. And yeah, so that's what we have at the beginning. And then well, I just implemented here the 2 steps I mentioned. So we know that the item we are looking for is in this index number 17 here. So now let's do what I promised. So let's flip here the sign of that item. So that's everything, just minus whatever you had originally here. And okay, we are then drawing something again. And then the second step here was to take the mean of all the probability amplitudes and now apply the formula that we showed. So 2 times mean minus the whatever you had originally in this table. So this results in a new array of the probability amplitudes. And then we can graph this what happens here. So so yeah, here you can see now on the left-hand plots after the phase inversion. So you can see this one now gets flipped in sign, and then after the second step, now you can see that now this guy gets back up here, and probability of that item is now something like 13%, like shown here. And then you simply continue. So again, like do the phase inversion of that one, and then do the reflection about the inversion about the mean. And now you see the probability is increased to 0.33 here, and so on. And finally, let's say in this case, after 5 iterations, you will get here up to, let's say, 96% probability to measure now the item we are searching for, and well, 1 minus that collectively for all the remainder. So very likely if we would now measure this, we would find here the marked item. So I hope that was clear enough. I mean, don't care about the details. The point here is just this, to demonstrate this phase inversion, and then the inversion about mean, and that we are alternating between these 2 steps. And then what it's doing here to the marked item is that it's amplifying the probability amplitude and de-amplifying all the rest at the same time. Okay, so I hope that yeah. So you can obviously play there with the different values if you get bored. So now let's get back to that by PowerPoint. Yeah, so that something like, yeah. So let's just say that we are convinced that this idea works. It's fine. But now, of course, like here in this code, I used the cheating trick. I used the information where the one I'm looking for it gets amplified. So it's not really not really very clear what is happening here in reality. So now some more details how this works. So yeah, so this is the 2 steps. But now how this would work in principle. So so now so suppose that this is now the general state of the system during this Grover iteration, well, then this what we indicate here by this W ket is now the winner state, the one that we are looking for. So and we know from the promise problem that there is exactly only one of these this possible states. So just one item we are looking for. So so now how this gets started is to create the equal the uniform superposition using let's say you have a you have a small number of n qubits, and now you apply Hadamard gate to each one of the qubits. So that's another notation we haven't really discussed, but this means, you know, apply the Hadamard tensor product of a small number of n Hadamard gates and apply to, you know, tensor product of a small number of n zeros. So just to clarify, for instance, this one, it means 0 tensor 0 tensor etc. tensor 0, and this is n number of times like this. And well, this is also the Hadamard, the matrix. Well, it's actually known as a Kronecker product in linear algebra, but it's something like you have the n Hadamard gates, and we take the tensor of those. So again, don't worry too much about this linear algebra part. The point of this one, as you know already, is that okay, what we are going to end up is a kind of like a superposition of all the possible different states. So I'm not sure. Maybe we can briefly remind what this means. So here. This enumeration in the sum, it goes through all the possible 2 to the power n states. So again, like pay attention to this innocent looking sum here. So this means that x iterates over all the possible n-bit binary strings. So this here, the sum goes through over all the 2 to the power of a small n number of different number of gets. I mean, including the well, if it's just a if it's let's say if n equals 2, then it's going to be, you know, those 0 0 plus 0 1 plus 1 0 plus 1 1, and in that case we have here the normalization term to make sure that everything is you know, properly normalized, okay, that the probability amplitudes are summing up to 1. So yeah, that's what Hadamard does, as we know, creates equal superposition over the possible states here. Yeah, the flat histogram, if you prefer. So now the idea is that, you know, the general state that we have created this way. So we can actually, even though we don't know what the W is, we can still decompose, you know, artificially decompose this sum into the term that contains only that thing we are looking for, the W, and all the remaining things here. So let's see how this is done. I mean, this is going to be very sketchy, but I just want to give you the general idea how this is done. So yeah, so let's say this is the general state, and this was what I just denoted. So this is the 2 to the power of n, and well, x goes over all the possible binary strings 0 1, and we have here the x. So that's the quantum state. Quantum parallel state, if you prefer. You know, it's now there is some probability amplitude over all the possible 2 to the power of n states here. And so now we can rewrite this so that, well, okay, maybe I will, well, okay, let's keep it this way. So this well, okay, I'm somehow like sometimes tired to write this 2 to the power of n, so let's just remind. So that was the relation, the number of bits and the number of states. So I can just you know, put here 1 over square root of n here. And now what I'm gonna do here, well, this is just a sum, you know, sum over some state. So I can certainly take the one that we are interested, the winner state here out. I mean, it's gonna be one of these 2 to the power of n things here. So so I just like I can write 1 plus 2 plus 3 plus whatever here and take one of the things out and all the remainder. Okay, so nothing special here. I can always take here the one that we are looking for, which we don't know, but I can certainly write in this way that this is the winner state, one of the 2 to the power n states we are looking for, and then the sum with all the rest. So I will just this time, well, let's say that x is not the w, everything else except this one that we are looking for, and let's say like that over here. And now what we do here is that, okay, we kind of like artificially, well, okay, this is just again some mathematics, but well, let's see how this is done. So I'm gonna have this 1 over square root of over n here, but I'm gonna also like artificially add here something like n minus 1 over n term here, and then okay, so now you can see there is the 1 over square root of n here at the downstairs from here, and then we have added you know, artificially put here square root of n minus 1 over here. So now in order to get rid of that artificially added thing here, well, in mathematics we do all the time this kind of tricks, you know, you are adding and subtracting something to make or you are multiplying by something and then dividing by that same number to get rid of that one. So everything is legal here, nothing mysterious. So we have just rewritten this in a different way. So again, all the rest except the one that we are looking for. So and now actually well, now you can perhaps see the reason why we wrote it in this way. So this is now the kind of like, it's now the equal superposition of everything else except the one that we're looking for. You know, we are subtracted here the 1, so this now contains capital number of n minus 1 states because we removed the one that we are interested. So this is the uniform superposition of everything except the one that we are looking for. So apart from that term here. So we can perhaps give us some name. So if again, like maybe if you don't like the get notation, so just think about it as a vector. You know, what we are doing there is to sum up this 2 to the power of small n dimensional vectors here. But okay, we're forming here the linear combination of them. But in the end, you know, it's just some vector that is formed by this basis, like a computational basis here. So how about we, you know, how about we give this a name? So let's call this one whatever we got here like R, just for the rest. So it's just some one vector in the end when you collapse this sum here. So now what you have here is 1 over square root of n times the w plus now the this one this time here, so 1 over n minus 1 over n times the rest. So that's the kind of like manipulation we have done so far here. So again, there is no quantum black magic or anything happening here. We have simply stated, rewritten the general state of the system here in breaking it down into this W we are looking for and all the rest. By the way, is this a valid quantum state? How do we see it, if that's the case or not? Anyone still remembers how do we check? Just in case we are sometimes unsure. So what should we do here? Yeah, so we take here the alpha modulus squared plus beta modulus squared equals 1. And well, yeah, this squared equals 1 over n. This is n minus 1, 1 over n. So when you add up to 2, so you should end up with 1. So yeah, I mean, okay, I see there is a question. So please, Kulsum, go ahead. Was there a question? Okay, maybe not. Okay, so okay, we better move on. So yeah, and now actually the one of the ideas is that okay, these two vectors, you know, it's just we can easily visualize this in a 2D. So these two vectors happen to be orthogonal to one another. So you know, if W is pointing, let's say, you know, if we have a coordinate axis, let's say okay, let's say W goes on this side, and let's say the R goes on this side. So we can easily visualize this in a 2D. So it's going to be some kind of like combination of these two vectors. So let's say, well, let's say it's going to be like that. It's in 2D we can think about this kind of like linear combination of two basis vectors W and R here. So maybe we should indicate like that. And well, this now leads to the already close to the ideas what we are doing. So now, well, we are simply gonna be reparametrizing here the probability amplitudes using an angle parameter. So let's call this sine of some theta of W, and plus then we have here cosine of theta times the R. And again, like what we have simply done here is where we define these two. So, you know, we're just agreeing that now, let's say sin of theta in this case is going to be 1 over square root of n. Okay, we could even use the special symbol defined as cosine of theta is defined as n minus 1 over n square root. And yes, so once again we seem to be back to the talking about the angles. I mean, I know I promised in the Blocksphere lecture that we are not going to be returning to this one, but it seems here it's actually useful. So again, if you now remember the unit circle, so to speak. So so yes, so maybe at the beginning, you know, you can see here that this well, the capital N is potentially going to be very large, right? And so this 1 over square root of n is going to be, well, it's going to be nearly 0. So let's say this is going to be some small number. So let's say close to 0 at the beginning of the iteration. And likewise here, you know, we have here almost like n divided by n here. So this one equals 1 in that case at the beginning. And now if we remember again the our favorite unit circle, so here then the well, we are going to have here some angle. Let's say this is the theta angle, and again the cosine is going to be here, and the sine is going to be here on the y coordinate. So at the beginning of this iteration, this s vector here is going to be, you know, it's almost going to be you know, very close to this the rest here, because well, intuitively the contribution of this item that we are finding is like a very tiny. So it's almost like an almost like to the direction of this r axis in this case here. And well, okay, so that is just reparametrizing the thing. And let's see if I have sufficiently clean notes to continue here. How do we do the actual phase inversion? So yeah, so okay, I think we probably just give me a second. let's add one more slide here. Yeah, okay. I always tell that it's risky to try something in real time, but I really want to give you some kind of like confidence that this whole thing makes sense. So now how to do the phase inversion? Okay, so that was the one that where we used the cheating trick in the Google Colab code. You know, we flip this sign of the item we are looking for. But if you still remember the phase, what happens to the phase when we go to the Oracle circuit? So that's the kind of like trick we are going to be using here. So okay, this is going to be sketchy, but you know, after we call the Oracle, so now okay, so better indicate this. So this is the Oracle matrix. And it's operating on this whatever state we had, this what we indicated by S. And well, let's just see what we had for the S. So we had a sine of theta times W plus cosine of theta times R. So so we had UF times the sine of theta W plus cosine of theta R, like that one. And now for the if you still remember how the Oracle works, so it was the -1 to the power of the fx, right? I mean that was the thing what we had in the, you know, whenever we have a state x, and now this is sent to the through the Oracle. So this gets mapped to -1 to the power of the corresponding function times the original state there. So that's what the Oracle does. And this time, if you still remember how we defined in this Grover search algorithm, the f function was exactly that, you know, it equals 1 whenever we have the correct item, okay, and 0 everywhere else. So what does this mean? So it means that because we know that, you know, the Oracle is now operating on, well, everything is here linear. So let's just put all the steps. So we have now the Oracle operating on that guy over here, plus the Oracle operating on okay, come on, UF times cosine theta R. Okay, and now we know that well, this is the one that we are looking for by the construction we did. I mean, the W was the one for which the F is going to be outputting the value 1, and otherwise it's going to be 0. So now we simply apply here the Oracle, the phase Oracle, if you prefer. So here we have the minus sign to the power of this function value, minus sign times 1 times the sine of theta times the W plus minus sign -1 times to the power of 0 times cosine theta times R. And this is because now, well, this was not the item we were not the state we are interested. So it's going to be the f value here is going to equal to 0. So here this is just going to be 1, and this is going to be -1. So in short, what you have here is now minus sine theta times W. So that is the phase flip that we did here, and plus the cosine theta times R. Okay, so there you have it. You know, now you see that I mean, this time we just use the property of the Oracle. We are not cheating like in the Google Colab code that I showed, but you can see that when you now apply the Oracle circuit to this arbitrary state here, what it's doing, it's gonna flip the phase of this item we are looking for, and not gonna do anything about the phase of this second, the remaining terms here. So yeah, this is the, okay, let me repeat. So that is the, okay, wait a minute, where do we have it? So that's what we did in the cheating operation. So we the probability amplitudes of all the rest are you know, we are not changing them, but for the one that we are searching for, we flip the sign here. So instead of the cheating thing here, you can see that when we apply the oracle to this general state, that's what we see here happening exactly. So that is what we wanted to have. I hope you can somehow like see the connection here. That okay, it makes sense. And well, I promised the geometric argument. So again, like well, this is something like I don't have a time to go through, but there is this particular operations that we are then implementing when we actually implement the Grover algorithm. So what the inversion item is going to do something like, okay, it's going to rotate. Well, suppose that this is your original state here. So it's going to be doing some rotation like that here, you know, invert. And then after the reflection by the mean, the second step, it's going to be a move to here. And then you will kind of like continue from here, a similar process. So after, you know, so similar what happened with respect to this axis here. Now you can think about, again, like, okay, there is going to be something like reflection. You know, we're going to be shifting. Yeah, this guy, well, okay, I'm doing terrible drawing, but, you know, it's first shifted this way. And then after the second step, it gets then again gets rotated here and so on and so on. And finally, this state, what you're looking for is finally going to approach the state that you are looking for, the W state. Okay, this is a very bad explanation, but if you, and there are different ways to get intuitions about the Grover. One of them is this simply geometric ideas, but you can also go through at the algebra level to see what is the when you detail what are these actual unitaries here that you need, is to get yourself convinced that yes, that's what happens. It's going to rotate slowly but surely the probability, well, the state, it's going to amplify the probability amplitude of the state we are interested and de-amplify the remainder. Okay, I think, yeah, okay, so it's already 1:45 soon. So let's see if I want to start anything else. Well, well, I think we got still 2 minutes. So so now we are done with the Oracle or the Oracle algorithms and the search algorithm. So now perhaps the useful algorithm, like I mentioned, historically being very important to quantum computing, is the Shor's factoring algorithm. So this one was again the algorithm to find, let's say, if you're given, let's say, given number 15, so what are the prime factors? So in this case, it would be 3 times 5 as an example. But in general, for like arbitrary integer, you can find the factorization into these primes and different powers there in general case. And the problem why this problem is of interest is that, okay, it's in use of those cryptography systems, as you probably already know, and it's believed to be hard, you know, if you, okay, 15 is easy to factorize, but if you are given some huge number n, and now you're kind of like asked to find the prime factors, that is assumed to be a very difficult problem for the classic computers. And then what this Peter Shor did in 1990s is that he figured out how to make use of quantum computer to, let's say, solve this problem efficiently. And this was historically one of the, I believe it's one of the reasons why the quantum computing is got a lot of interest and excitement. And nowadays, why organizations like the NIST are talking about the post quantum cryptography and topics like that. So, but again, like here, we're just going to be looking at we're not going to be discussing the cryptographic protocols. It could be actually one topic for your project if you are not sure yet to find one of these. But let's just, well, okay, let's talk about this SOR algorithm. I will give this explanation I promise to give this in 3 minutes, and then let's say next week if we want to continue with more details about this one. So I just want to sketch you the idea how this works. So yeah, so we have to talk about modular arithmetics first. So modular arithmetics is something where things are kind of like circling around, and well, clock is the most everyday life you are familiar with. So for instance, the midnight is the same as the noon, but with the when we take the modulo 12 like arithmetic. So and 3 in the afternoon is the same as 3 in the morning when we consider the modulo 12 arithmetic. So things are wrapping around after we have went through the full circle. And if you are a programmer, you know how to do this in Python. So to get the remainder, well, this operation divides the first number by the second one and prints the remainder. That's what we have here, the remainder in the modular arithmetics. So now the relevant subproblem in this SOR algorithm is something more general. It's called modular exponentiation, and in this case, there is something like a sequence like that, and we are where a is some number and n is the number we are interested about factoring. And now we are taking the powers of this a to the power of different integers, 1, 0, 2, etc. And the interest here is to find that, okay, what is the period of this sequence? So I think I'll have to stop it here so that we have something to talk about also next week. But basically, when you do this kind of modulo operation here, so you know, you get some number of some number a, some number n, and then you know write a for loop over these different powers here and compute the remainder using modulo operation. You will find that this sequence of the numbers will be periodic. Actually, it's repeating itself, just like the clock is circling around itself. You will find that this sequence will kind of like repeat every few kind of like circles. And the task here is actually to find, okay, what's the repeating period? So what's the how often this sequence repeats itself? And I'll stop it here. So next week we can also talk a little bit of the SOR factoring algorithm. So for the time being, you can just think that this problem, when the a and n are not too large, you know, you can just solve it shown in a classical computing. But in the SOR algorithm, the numbers we are dealing with are very huge, and particularly this a to the power of x will explode very quickly. I mean, you will run out of your computer memory even with not so large numbers here. So when you compute this kind of modulo arithmetics, you don't want to compute it directly in the way we would do here. It's not going to be possible. You will run out of memory and so on with very large numbers. And well, this is the key part in the SOR algorithm that the quantum computing is helping to solve, how to compute this the period of this modular exponentiation sequence. But okay, I think let's stop here, and so next week I think I will just give you about the SOR algorithm, just a sketchy version. I mean, we're not going to be really going to the very much detail, because this would require introducing quantum Fourier transform. I know physicists here would be probably happy to hear, but I know that the average computer scientists are not so maybe so willing to take yet another new mathematical tool, which is actually generalizing the Hadamard transform. So I think I will next week I will just give you the brief idea, and then hopefully one of you actually could then pick maybe the Shor algorithm as a topic for the project if you are not sure yet, and to tell more details about it. And otherwise, next week, so we will not have any more the mandatory quizzes or anything, but I'm possibly and so there is not going to be homework for next week or homework quizzes either, but I'm possibly gonna be adding some bonus quiz or something like that you still have let's say some interest to come next week. So what I plan to do is complete the Shor and maybe tell briefly about the quantum machine learning a little bit, area I'm personally interested about. But okay, let's end up here. Sorry to go over time again, and see you then. I think on Friday, and please remember it's starting 15 past. Okay, Sami or Pirkka, any last announcements? Okay, everything is clear. So you already know you have to pick the project topic this week. So, okay, so thank you, and see you on my side next week then. Bye-bye.